Hi, good afternoon. Am I audible and the slide is visible? Can you hear me? Okay. Where are the rest of the guys? Why there are only 12 people out here? Where are the rest? Only these many, huh? Prakhar, Rajneesh, roll number 176, 185, 198, 241, 261, and 104. Pulkit and Palak, kindly add your enrollment numbers also, right? Beside your name. I mean, in front of your name, preferably. Shall I start? Shall I start? What do you say? Okay. Sure. So, uh, in our last lecture, you guys are BY. So, in our last lecture, we were here. We were here. And even though this is a good example, but it would have been better if you have straight away shifted to the example which was given us like few minutes back. But I'll start up with this itself. Now, what you got to do is you have to just see this part. Proof that proof of the fact that Socrates is mortal. Right. So now, in statement one, Socrates is a human. This is the predicate of that sentence, and it is a fact. Right. Now, X is mortal if X is human. Right. This is a rule. That means this is one of the facts that has been given to you. There is one rule that has been provided that if X is human, then X is mortal. Now, there is one assumption that means you can call it as a forced rule, in fact. It talks about like Y is not mortal, right? Y is not mortal or Y is immortal. Fine. Then, if somehow there is a fact or rule or an assumption which states X equal to Y, that means X is obviously a human being who is mortal, and I have said that there is something called as Y, which is same as that of there is something there is something called Y that is same as that of X. Now, I'm saying if this is the case that has been either given as fact or rule or an assumption, then my next thing is by combination of from 2 and 3 I can come to a conclusion that Y is not human, right? Why Y is not human? Since Y is not mortal, that means Y cannot die, so Y cannot be human. And then again there is something we have assigned from 1 and 4 unification. It is that Y is Socrates. So there is a contradiction that comes up if you check the rules or if you check the statements in sentence number 5, 4b, and 1. right? So until now, in our forward and backward chaining searches previously that we had, we never had these kind of situations when there are contradictions, right? When there are contradictions. Now let us see how things proceeds in actual examples. Don't worry, I'll be giving a good amount of time in those areas which I feel is important and that is not straight away theoretical, right? So this explanation is just what I have said you now. Now, I'll not talk about what is forward chaining, that is data driven, and what is backward chaining, which we call it as the goal driven. Rather than, we'll be straight away shifting to we'll move on to this example. Now, very precisely, keep on just listening and watching. There are a few set of rules that are given to you. There are a few set of rules starting from rule 1, rule 2, and until rule 3. And we do have certain informations that are provided. That means we call them as facts. These are something that are, we can call it as axioms, right? Some rules are given. What are those rules? Now, if it is hot and smoky, then there is a chance that there is fire. If it is hot and smoky, then there is a chance that there is a fire. If the alarm beeps, then definitely there is smoke. So rule number 2 says if the alarm beeps, there is smoke. Now, if there is fire, then you have to switch on the sprinklers. If there is fire, then you have to switch on the sprinklers. Now, I have got few facts. Facts means a working information, or in fact, to be more precise technically, a working memory. In the working memory, that means the thing that is happening right now. What is happening? Now the alarm is beeping or the alarm beeps and it is hot, right? These are the things that are given. Now, these are things that are given. The same thing, we are coming down here in the same example. If you see, the only difference between these two examples is that the rules are remaining the same. The facts are also the same. The only thing is that here we do have a premise and a conclusion, right? We do have a premise and we do have a conclusion out here. In this case, we do have a premise, we do have a conclusion, and we do have an act to be performed. Like if it is hot and smoky, then you can add an information called fire in the working memory. If the alarm beeps, then you can add smoky to the working memory. If there is fire, then you can add switch on the sprinklers to the working memory, right? I'll not be saying again that this part is the working memory because we have got another diagram where we'll be explaining all these things. Let us move on now. Now, here, the overall set of rules, they remain the same as we have seen in the previous two examples, right? They were just, simple examples. Here, there is a solution for a forward chaining actual practical life problem, right? So we do have a few rules out here. If it is hot and smoky, the same thing. And fire, if the alarm beeps, it is smoky. If there is fire, then switch on the sprinklers. And there are two facts that are given, fact 1 and fact 2. That means alarm beeps and it is hot. These two are given. Don't get confused by fact 1 and fact 2 and the remaining facts. That means fact 4, 2 and 6, fact 4, 5 and 6. This is a small error. This is 5. This will be 5, right? Now, you can see one thing that this is my rule segment, rule base. This is my working memory, and this whole overlapping part, I call it as overlapping part, it is my inference engine, right? Or this is the inference making area. And these are the added facts from the already given working memory when applied to the set of rules that are been provided, right? So now let us see what is happening. Now we do have alarm beeps. We do have alarm beeps. What we are going to do is we'll be scanning from rule number 1 until rule number 3. Yes, is there a atomic premise part for this? Yes, we do have alarm beeps, and this thing will add an information called smoky. So from alarm beeps we are adding smoky as fact number 4. That means by using fact 1 and rule R2, by using fact 1 and rule R2, we have added this smoky. Now next one is, this 5 is what? Now we'll be picking up this hot and we'll be scanning for whether there is something called hot. No, it is not there, it is not there, it is not there. You can say that yes, it is there, but there is a combination of hot and smoky that is to be there. So I have to check out in my working memory. What is my working memory right now? My working memory is F1, F2 and F4 after first iteration. So now I have got extra information called smoky. So now I can add up hot and smoky. That means I can add up hot and smoky here. That means F2 and F4 can be added up, and by using rule 1, F2 and F4 in addition to rule 1 will give me what? The fire. That means hot and smoky will give me the fire out here. Now comes what? By application of F2 and R3, by application of F2, that means this one, it's been wrongly given. F2 and R3, what we are going to get? It is switch on the sprinklers. So you can deduce further facts. That means you can infer some more information by the already provided facts that are given and the set of rules that has been provided to you, right? So this was the case of forward chaining. What happens in case of backward chaining? Now I have got a set of rules here, all the same rules that are there in our previous problem, and with those same rules I am again provided with a set of facts, and from those facts I have to answer a question: should I switch the sprinklers on, or in fact I can also validate a statement whether the sprinklers has to be on or off. That means I can prove the case of sprinklers being on or sprinklers being off for the given set of facts and the given set of rules that are there, right? Wait, there are a lot of people waiting in the lobby. Okay, now let us gradually move again. Now here you can call it as the basic architecture for the forward chaining mechanism. So the forward chaining system has got certain properties, algorithms and conflict resolution strategies, and they are illustrated in this diagram. What are there in these diagrams? Now we do have a rule base. What are these rules? These rules are very precisely as I have shown you here. These rules are these rule 1, 2 and 3. Here rule 1, 2 and 3, and also in the previous problems, right? These are the rule base. Now there is a working memory. Working memory is the set of facts that are given, right? Working memory are the set of facts that are given to you. Now there is an inference engine. That means a further created set of information by application of working memory and application of rule base. The added informations are in the inference engine, and also we draw further more facts from the provided facts and the rules, and we generate more facts via this inference engine. Generally we call it as the shell. Okay. Now facts are held in the working memory. There are certain condition action rules that represent the actions to be taken when specified facts occur in the working memory, right? So these are again some of the things which you already know. Now there is an important thing that is coming up. Kindly pay attention. Like, there is an algorithm for forward chaining. We have to repeat these steps successively until we have solved everything, or there is no condition match. Now let us start up with what we are supposed to do first. collect the rule whose condition matches a fact in the working memory. Collect those rules whose condition matches a fact in the working memory. What you got to do here is collect a rule. That means you have picked up a fact. The first fact is alarm beeps, and you have to catch hold of the rules which matches with the working memory. This is the working memory part, and there is a rule that matches exactly with that of the working memory. And you'll be adding this further information that has been generated by the matched rule with the working memory, which generates further information. That means add Smoky, and I'll be adding that to the working memory. This is my second statement of the algorithm here. See, now collect the rule whose condition matches a fact in the working memory. Do actions indicated by the rule. That means add Smoky. This is the action that is indicated by the rule. And you have to add those facts to the working memory. We have done that. Or there is a new thing that you are seeing for the first time. That means deleting the facts from the working memory. Now, until the problem is solved or no condition matches. Let us see how we can apply this. Yes, students, kindly call the rest of the guys also to be there, because I have to take the attendance, and these things can be seen at later stages. I'm saying you again and again, this is not a paper-based attendance. I have to submit all of them, right? I have to prove that the student was present. Right, even for my video lectures also, I had given you assignments, so I have to somehow justify that these many students were there, right? So please turn up, and I'm feeling really sorry to say that even if you're not feeling like listening, at least be here, and just put on your phone at least, and log into the WebEx, and after that, as a teacher, I cannot say anything more. But kindly be there, right? Kindly be there. This is for your own benefit. This is for your own benefit. Right. Now, let us see. We got a fresh example. This example has got all the previous set of rules and two extra rules and one extra fact, right? We have got two extra rules and one extra fact that has been added. Previously, we had three rules. Here we do have got five rules. And previously, we had two facts, and here we do have one more fact. This could have been F3 also. It doesn't make much of a difference. So the first one is hot and smoky, then add fire. The next one is alarm beeps, then it is smoky. If it is fire, then switch on the sprinklers. If it is dry, then switch on the humidifier. If the sprinklers are on, then delete dry, right? That means not that at all occasions I have to keep on adding an information to the working memory. There can be certain situations where you can even delete the information from the working memory. So let us see how these things are done. So let us begin with by picking one of them, like alarm beeps. Then what is the thing that I can add? Add smoky. So I have added it up here, right, from rule number 2. I have picked it up. Then there is something called as hot. I cannot match up anything out here. So the next one is dry. Do I have anything for that? Yes. For dry, I can add something called as switch on the humidifier. So I have added switch on the humidifier here. So I have added two informations like the smoky and switch on the humidifier, right? How we are doing it, as I have said you, these are mentioned in the square braces inside, right? Now, what you got to do next is, here you can add fire also from F2 and by application of R1, by F2 and application of rule 1. That means F2 and R1, that means hot and smoky. If I am hot and smoky, if I am adding up, I'll be getting this fire out here. Now, the moment there is fire, what you can add is, the moment there is fire, what you can do is you can switch on the sprinklers. You can switch on the sprinklers, right? Now, the moment the sprinklers are on, as you can see here, by R3. So as the sprinklers are on, you have to remove another thing. That means you have to delete something. That means dryness. So the moment the sprinklers are on, you have to delete this segment of fact or information that is there in our working memory that has been provided to us, or that is there in the given section. That is there in the given section. So by doing so, what we have got here is there is a conflict. That means we have to delete certain amount of information that has been already provided in this factual part, right? That means in this working memory part. So these are the initial cases where you can see a conflict coming up. So what can be done here? Now we have a modified forward chaining algorithm, or the forward chaining algorithm 2. The first time remains the same. That means I have to repeat all these steps until we reach for our goal condition. That means collect the rules whose condition matches facts in the working memory. I have said you previously what you got to do here. Now if more than one rule matches as stated above, then there is here we have got more than one rule that has been matched, and hence there is a conflict. So we have to use conflict resolution strategies. There are certain ways out to resolve these conflicts, to eliminate all but one, right? To eliminate all but one. Wait. Okay. Now, what are the conflict resolution strategy? So, whatever you forget or you remember, one thing you have to definitely remember, that is, just a moment. So our conflict resolution strategy does have three parts, or three ways by which conflicts can be resolved in our these kind of conflicting situations while dealing with forward and backward chaining. What are they? They are refractory, or recency, or specificity. What do I mean by refractoriness? That means stubbornness. That means sticking to a particular place, or refractory situations, right? Recency means how recent anything is, and specificity is how specific things are. Now, in case of refractory part, a rule should not be allowed to fire more than once on the same data. This is the same thing that has happened for the sprinklers. When the sprinklers and the humidifier, they were there, so there was a repetitive surgeons, or a repetitive what should I say, they came up twice, and that's the reason why there was a conflict under this case. So this was a typical case of refractory situations. So you can avoid this by applying refractoriness or recency. That means the rank instantiations in terms of the recency of the elements can be clearly defined in the premise of the rule. That means the preceding part of the rule, the premise and the conclusion. Premise is the initial part, conclusion is the remaining part of the rule. And specificity. Specificity is what? Specificity is the rule which have a greater number of conditions, and we are therefore more difficult to, and they are becoming more difficult to be satisfied, right? Fine, you'll be going through this part. It is nothing. They talk about the theoretical concepts of meta rules. Fine. And this is our backward chaining and forward chaining algorithms differences. If you see the condition diagram of, if you see the condition diagram of them, then you can see here there is for smoky, and the fire alarm beeps, and if the sprinklers are on when there is fire, and when it is hot enough, right? So encoding rules are there. What we're talking about, it's nothing, it's over. So for us, the knowledge representation part is over. We'll just be reading this control knowledge. It's nothing. So our knowledge representation part finishes here, right? So we are closing this part. Now, we'll start up with the next chapter. That means the expert systems, right? We'll be starting up with the expert systems here. So, in expert systems, what are the things that we'll be going through? The topics will be the basic introduction part. Then we'll be talking about the knowledge acquisition. We'll be talking about the knowledge base, the working memory, the inference engine, then expert system shells. It's a little bit of explanations and application of expert systems. Yeah. So, right. So let us see gradually. Hey, you can see the screen now. It's visible now. Don't sit quietly. Tell me. Hey, you can see the screen or not? Okay. So let us begin with what are export systems, right? So how would you put up the first definition of an export system? It is basically a kind of HCI or human computer interaction tool or an interactive platform that is computer based and that can help out in making decisions, and also it can help in uh, introducing both facts as well as heuristics to solve certain problems and also make out decisions. Okay. So an expert system is also a model, an associated procedure that exhibits within a specific domain a degree of expertise in problem solving that is comparable to that of an human expert. There's a term called expert. What do we mean by the system being expert? Now, today there are a lot of learning algorithms, there are a lot of machine learning algorithms, there are a lot of techniques by which we can train a system. But initially, the first step of making a system learn started up by making the system an expert in certain domain. Believe it or not, but expert system is the first ever practical application of the AI base and the first ever decision making tool by by use of rules and inference knowledge, right? So in a nutshell, you can just see it here, like an inference engine plus a knowledge is an expert system. In our previously captured information from our previously captured knowledge, we can say that algorithm with data structures, it is the program in traditional computers, right? Anybody who talks about an expert system, anybody who talks about an expert system will definitely talk about Dendral, right? Dendral was the first ever expert system that was generated way back in the 1970s at Stanford University. Now, the expert systems are computer applications which embody some of the non-algorithmic expertise. Why they are called as non-algorithmic expertise? Now here it is totally rule-based, right? They are totally rule-based, but at times you can have certain amount of quantification to the rules, right? We provide certain amount of quantification to the rules. We'll be talking about it gradually. Now, for an for example, expert systems are used mostly in diagnostic applications or in decision making. They can even be useful in playing games like the chess, right? Sometimes they can help you out in making financial decisions, or they can help you out in configuring the computers. Just a moment. Every now and then I have to admit somebody who is waiting in the line. और कोई है who's waiting in the lobby? Okay, so now before we move, I'll tell you a very small story about these expert systems. Now, out of the 17 or 20 most powerful formulas that has been ever developed by human beings, one is the Midas formula. Midas formula. Midas formula was developed by Black and Scholes, right? Midas formula was developed by Black and Scholes. Now, why I am hatching the story out here? Because you need to understand what is this expertness for an expert system. So, something that happened during the 60s or 70s, when the market started growing and there was globalization all around in most of the countries and in all the continents. So, gradually people came to know that if they invest in the markets and it can fetch them good amount of money. But as we all know, there is a huge amount of risk that is always associated with investment in the markets. So, uh, since those uh, since those risks were there, so many of the people they came up with certain ideas that how they can somehow tame the market and can give better guesses to their customers so that they can not just customers for themselves also so that they can make out more and more money. Nobody has seen tomorrow, but you have to make wiser predictions for tomorrow so that your uh, your you don't sit back in your you just don't sit back in your future and curse your past, right? So to make the financial decisions, Black and Scholes, these are two scientists who came up with the Midas formula, which gave a wonderful, a fascinating theory by which people can put up their money without much losses and they can thus increase their profit margin. How they did it? They did it by using a technique called as the dynamic hedging. That means you don't just pay your whole sum of money for the crashing of the market, but you pay a small penalty, right? And there is a limit that has been fixed between which the prices of that particular bond will fluctuate. This is what can be done by going through the record of that particular financial institution over quite a long period of time. And these kind of dynamic hedging techniques gave rise to a new profession of the 21st century. We call it as the hedge fund analysts. Hedge fund analysts, right? So whenever you see somebody who's an hedge fund analyst working for, say, Lehman Brothers or Ernst& Young or some of the world's finest financial institutions, remember they are all expert in their financial domain. So likewise, Black and Scholes, they came up with a formula and people invested like anything and they gave fantastic profit to their customers. But early in the 1990s, when USSR crashed and everything changed and things were like topsy-turvy. So uh, these kind of experts ideas can be incorporated in a computerized system so that so that they can be for the benefit of the masses. They can be for the benefit of the masses without much intervention of the human knowledge. So the expert system now will be talking about its human interfaces or human or the components of the expert system. Expert system basically does have a knowledge base. They do have a working storage. They do have an inference engine, and they do have a user interface. Now, this first we got the knowledge base, the working storage, the inference engine, and the user interface. There are around four human interventions that are there in this particular expert system. The first one is user. User has got no role to play. In fact, they are just the end users who can use this whole of the expert system for his own benefit. Now, there is another person who is the domain expert. The domain expert is not a technical person. He is just having the expertise in his particular domain, right? He has just got the expertise in his particular domain. Maybe he's a financial expert, maybe he's a medical expert, maybe he's from an architect. He's an architect, or he's having an architectural expertise, right? So the domain expert is somewhat like this. There's a knowledge engineer. There is one person. The knowledge engineer's work is to encode the information. That means extract the information from the domain expert and then encode it and then add it to the knowledge base, right? There's a system engineer who takes care of all these three tier of the export system. That means he takes care of the functionality of the knowledge base and the working storage. He also takes care of the inference engine. That means how to draw the inferences from these two phases, and how he can put up the user interface in front of the user, those who are using it, right? Now, there are explanations for all these things in the next slide. So these two individuals, that means the knowledge engineer as well as the system engineer, they can be the same person or two different person depending on the size of the expert system. So components and interfaces. What are the components that are there? Now we do have the knowledge base, we do have the working storage. In the knowledge base, we do have the declarative representation comprising of if-then rules. In the working storage, the data which is specific to a problem, specific, that means that is being used at this present time is for solving the problem, is stored in the working storage. You do have the inference engine. That means the code at the core of the system which derives recommendations from the knowledge base. That means this is basically the decision making part which utilizes the working storage by the use of this knowledge base. And the user interface. The user interface is the place where the user interacts with the expert system. Now, the roles of the individuals who interact with the system. First one is the domain expert. The individual who currently are expert in solving the problem, they are called as the domain expert. Here the system is intended to solve, right? So so we do have the next one as the knowledge engineer. The individual who encodes the expert's knowledge, as I have said you a few minutes back, in a declarative form that can be used by the expert system is called the knowledge engineer, the user who uses the expert system. Now, in an expert system, what happens is mostly you have the expertise of a particular human, right? And he may not be availed all the time. And there are a lot of knowledge that is available, which is very specific to its application in a particular domain. Like a surgeon is preferred. That surgeon is preferred who's having a very long experience in performing surgery. If those things cannot be straight away, taught to an individual through books or bookish knowledge or from any other sources, the best thing that can be done is straight away extracting that information from that particular expert, and then you can model it in the form of an expert system module, that means AI based module, which can be utilized for solving problems of the same nature where the expertise of that person can be utilized, right? So there is something called as the expert system shells. There's something called as the expert system shell. In a nutshell, we can say that expert system shells are knowledge engineer and system engineer. That means out of all these individuals, The knowledge engineer and the system engineer, they are called as the expert system shells. They are called as the expert system shells. As I've said you a few minutes back, now depending on the size of the system, the knowledge engineer and the system engineer might be the same person. If it is a smaller expert system of smaller domain, then we can say that the both the person can be a single person who can play the role of both the system engineer as well as the knowledge engineer, right? But if it is of a larger size, that means if it is of a mammoth size, then we can have two or more individuals who can take care of that. Expert system characteristics. Now, expert system characteristics are what? Now, they talk about how interactive the expert system is or how interactively it operates. The tools that have the ability to filter knowledge, these are the characteristics of the expert system. Make logical inferences based on the knowledge stored. Ability to explain reasoning. Ability to explain reasoning. Right? It is domain specific. Now, capability to assign confidence values. This is also one of the characteristics of the expert system. Then we do have the application, the cost effectiveness, right? Let us see one by one. What are they? Now, if we are talking about how interactive the system is, this means an expert system must respond to the questions. Obviously, this is what they are meant for, right? So they must respond to the questions. They can ask for further clarifications from that particular user who is using the expert system. They can even make the recommendations, or it aids in decision making process or steps. Here, I'll again stop for a few minutes and I'll tell you how it basically looks. I hope many of you might be using this Arogya Setu app. This is a very nice innovation of our government. Even though I'm not calling it as an expert system, but it has got a module where there is something that is said like you can yourself check whether you are having the COVID or you have a chance of having the COVID or not. So there are a set of around 20-25 questions which you got to answer. What is your age and where do you stay? What is your travel history? How frequent do you go out? And all these things, all these questions are there. And you have to keep on answering those questions to the system. And at the end, it will come up with like you have got very less chance of contracting this disease and this. These kind of recommendation systems or decision making systems are somewhat you can call it as an expert system, right? So this is one of the examples. There are some of the modules also which you can see in which there are certain boxes where you can take like whether you are having fever or not. Then there are certain interfaces where you can in many of the hospitals it is there, like whether you are having fever or not and whether you're having cough and cold or not. If the fever is there, then for how many days. All these informations they keep on collecting, and at the end they make out a kind of judicious guess that what are the percentages that you can have any particular kind of disease. So they can write down 3 or 4 or 5 diagnostic diseases, right? That you can have a 30% chances of having a flu or 40% chances of having normal cough and cold and fever, and these kind of things are there, right? So these are the decisions that are made by the expert systems, which has been encoded in that particular module by the domain expert. In this case, the domain expert is who's the domain expert, and the doctor is the domain expert in this case, right? You are listening or not? All of you are sleeping. मुझे ऐसा क्यों लग रहा है कि you are
No,
sleeping?
sir.
सो तो नहीं रहे हो ना?
No, sir.
बस ठीक ठीक ठीक. Now the next one is the tools have the ability to shift or filter the knowledge. That means storage and retrieval of the knowledge and mechanism to expand and update the knowledge. And another feature is they can make logical inferences based on the knowledge stored. The simple reasoning mechanisms, or sometimes you do have the knowledge base must have a means for exploiting the knowledge. These are things to transfer and the ability in reasoning, it remembers the logical chain for reasoning, and therefore the user may ask for that how come you have come to a conclusion that, or come to a decision that this is what you have to do or you don't have to do, right? Then it is always domain specific. Any expert system that you see is always domain specific, like an expert system for medical purpose, or expert system for some kind of financial decision making, or you can have expert system for some kind of other information where there is a particular domain, right? Many a times this has happened. Okay, now I'll talk about this after a few more minutes. Now we do have it should also have the capability to assign confidence values. This is a very important thing, right? What does this thing means? It can deliver quantitative information and it can interpret qualitatively derived values. What do I mean by this? What I mean by this is, let's say I have got certain parameters on the basis of which the decision is to be made by an expert system. Now, somebody is having cough, cold, flu, and running nose, and coughs, and high fever, all these things are there, right? So he can have a normal seasonal change kind of fever also, or he can have some kind of severe diseases. You don't want to take the name of that also, right? So those things are there. So what should be the percentage? What should be the kind of confidence values that should be provided by the expert system so that the user can understand, okay, this is the percentage by which it is endorsing that this person, say the expert system is saying by 90% accuracy that this person is only having a normal cough, cold, and flu, right? So these kind of confidence values are also a kind of feature for the expert system. I'll again come back to this domain specific part. I've been watching it for almost around 7-8 years now. That guys are coming up in the third year and finally with a lot of projects in which they talk about that I'll be making a chatbot and it can give any information. Remember, dear students, like any AI application base that you make out, they are mostly domain specific. And if you are making something that is very, very generic or can be applicable to almost anything, then that thing becomes really critical. Why? Because in domain specific, the way by which you populate the knowledge, it becomes very handy. Whereas in case of when you are handling diverse kind of information that is to be kept in the knowledge base, then this population, then this knowledge, or then this database feeding mechanism becomes very, very critical, and the way to handle this information also becomes very tough. So most of the time, this expert system is a domain specific one. Now we do have the applications of the expert systems. We're just going through the introduction part of it, right? Best suited for those dealing with expert heuristics or solving a problem, right? Where you do need a expert heuristic, right? That means they can solve a problem, but with how much accuracy, it is not known in most of the occasions. If you're having these kind of problems, then only expert systems can come up handy. They are not suitable to make out choices for those problems that can be solved using purely mathematical techniques or numerical techniques. Here you can have a very good chances of coming to a very accurate solution. So under these cases, we generally don't go for an expert system. The cost effective alternative to a human expert. In most of the cases, whenever there's someone who is very expert in a particular domain, let's say somebody is very expert in cyber crimes or in medical domain or ethical hacking, then that person charges a hell lot of money for making you understand his or giving you his knowledge or his expertise in fact. So the expert systems have become increasingly popular because of their specialization, even though they are restricted to a very narrow field. That means they are a specific domain. Encoding and storing the domain specific knowledge is economic process due to its small size, right? The expert system features. The expert system features are basically goal driven, that means they either backward chaining or they cope with uncertainty or they do have the forward chaining. They do have the data representation part, they do have the user interface, and they do have the explanations for that, right? Now, the most important things are how expert systems take care of this forward chaining and backward chaining. Coping with uncertainty is something that gives the ability of the system to reason with rules and data for the information that are not precisely provided. Right? Data representation, the way in which the problem-specific data in the system is stored and accessed. Right? So these things there. Now they'll start up with this goal-driven reasoning, and this is there, and this whole part is there. They have solved a small problem. So for BY batch, I have already shared a very exclusive around 40-45 minutes video lecture on this on YouTube. It's already there, right? It is already there, and this is there. And for data-driven part, this thing is also there. With the solved example, this example has already been solved and it is there. If you want that explanation to be there again in this class, then I can give it to you now, or else we can skip it. It depends on you. I have got this whole thing ready out here. ये मेरे पास है. This is my handwritten note of it, and I can go through it if you wish to, or else I can skip. I can make you understand this actually this problem that is there. One of the problem that is supposed to be solved. This is the problem of forward chaining, a very small and easy one. I could have given you a bit of idea if you wished, or else we can skip it, or if you wish we can go through it in the next class as you say. Shall we go for the next class, because today is Sunday, 1 घंटा हो गया है, and I won't disturb you further. Who's there for BY? BY में कौन है भाई? आ गया. Where is Swish? Swish, are you there? Swish Pratap Singh, please throw us attendance below. Pick up the attendance. Taken. वाह, ये solid लड़का है. चलो, thank you. You may go now. We'll go through this in our next lecture tomorrow or whenever it is, right? Chalo, bye. Take care. Thank you. You may leave. The attendance is already taken. You may go. We'll go through it again in the next. Thank you.